So yesterday we finished discussing the index on the level of linear algebra. We constructed the mean index, which is a map from the universal covering of SP2N to R, a homogeneous quasimorphism with suitable normalization, and the Conley index is a map from a certain part, an open dense subset of SP2N lying over the non-degenerate part the part without eigenvalues equal to 1. And the two are related. And what particularly matters for us is that the difference between the two is bounded by a universal constant, namely half of the dimension. And actually what we have here is a strict inequality when the endpoint is weakly non-degenerate, meaning at least one eigenvalue is not equal to 1. Not all eigenvalues are equal to 1. When all eigenvalues are equal to 1, no, I'm not saying it right. Let's just say when it is non-degenerate. Let's just say this. Because, you see, this part is defined only when phi of 1 is non-degenerate. So even to write this down, I need to require non-degeneracy. So let's keep it this way. Let's keep it simple. Non-degeneracy, yeah. So I require this. Not equal to 0. Thank you. Thank you. OK, now it's better. Now I think it's good. So how do we extend this linear algebra part to periodic orbits? Well, when we have a periodic orbit of one periodic orbit of a Hamiltonian, we have the, so call it X, we have the linearized flow along X, which is a map from one tangent space to another. So once I fix a framing along the orbit, I can identify both, well, all of these tangent spaces with R2n, and therefore what I have now is a path in SP2n. And by definition, the Conley index and the mean index of the orbit with respect to that particular framing is equal to the sort of, if I call this now phi t or phi, then the Conley index of the orbit or the mean index of that orbit are equal to the Conley index of phi and the mean index of phi. Now, Now there is an issue where to get this framing from. After all, there are infinitely many of them, and the result depends on the framing. So the standard way to do it is to fix a capping of an orbit. If you remember, the orbits are, all orbits we consider are contractible. So once I fix a capping of the orbit, this would be a map from some disk to W, which restricts to the orbit on the boundary. The tangent bundle restricted to this capping is trivial. Maybe I should say the pullback, to be quite strict. The pullback of the tangent bundle is a bundle over a disk. It's trivial up to homotopy, and moreover, up to homotopy, it's trivial in a unique way. So this is the framing I'm going to use. So there is a unique up to homotopy framing along a trivialization along the disk, and that's the trivialization we are going to use along the orbit. Now, the next question is, what happens if I take a different disk? If I take a different disk, V prime, then the ambiguity, the effect of replacing V by V prime is the, so going from V to V prime affects the indices, both of them, in the same way. Namely, the result is the integral of the first Chern class over the sphere obtained by clutching the two disks. Under our assumption so far, the first Chern class is equal to 0 on pi 2. So here, this is an element of pi 2. And therefore, the integral is 0, just because I'm integrating 0. All right, that's, and this shows that when the first Chern class vanishes on pi 2, in the index, either of these two indices of a contractible orbit is well defined. Now, the next little bit and a bit of Floer theory we need is a continuation map. I'm going to be very brief here. When we have two Hamiltonians, H0 and H1, we can consider a family of Hamiltonians, roughly speaking, connecting H0 and H1. Usually this family, well, I prefer to think about S as ranging in the interval 0, 1, but technically speaking, S ranges from negative infinity to positive infinity, being H0 at the negative end, H1 at the positive end. And this gives rise to a map of Floer complexes commuting with the differential. One important point to keep, and therefore a map of Floer homology. One important point to keep in mind is that this map in general does not preserve the filtration. Namely, what can happen is sort of that this map actually increases the action. But it increases the action by a controllable amount. Namely, sort of if let's give this name psi. So if psi of x is the sum of y's with some coefficients, because I'm working over Z2, these coefficients are 0 and 1. So let's just say sum of some orbits by i's. Then the action of H1 on y does not exceed the action of H0 on x plus the following constant. Here I'm taking the integral over s, and then the maximum over w, well, I have to take two integrals over s and t, of the partial derivative of h with respect to s and here dt ds. So if h is pointwise decreasing as a function of s, if, for instance, I go from a larger Hamiltonian to a smaller Hamiltonian, then this number is everywhere non-positive, and the action filtration is at least preserved. Otherwise, you get this possible increase of the action filtration, and what I have. So unless h sub s is strictly pointwise decreasing, then the action. And so the upshot is that when I look at the filtered Floer homology for some interval I, then the resulting map shifts the interval up by a constant, and the constant here is exactly that. So that's something to keep in mind, something we don't, when we think about the global picture, something that when we look at the sort of global Floer homology with I being the entire real axis, this shift just does not register there. In this case, of course, you can go in the opposite direction, and this becomes an isomorphism. So one more thing to keep in mind is what this enables us to do is the corollary of this thing is, first of all, the invariance of the Floer homology in general. But what this enables us to do, so is to define the filtered Floer homology even for degenerate Hamiltonians. So let's say H is possibly degenerate. And the endpoints of the interval AB are outside the action spectrum of H. Let's take a small non-degenerate perturbation. Then AB are still outside the action spectrum. And by definition, I can set the Floer homology of H to be the Floer homology of this small perturbation. And it immediately, sort of the difference between H twiddle and H is small, so the shift of action is small. The endpoints of the interval I are some distance away from the action spectra involved, so there is nothing here. And it immediately follows from the continuation argument that the left-hand side here is well defined. Now, another very brief remark I want to make is sort of what happens beyond the aspherical case. Again, my goal here is mainly to set conventions. So in this case, the generators are capped orbits. So every orbit now comes with a disk V, and two disks are considered to be equivalent if they have equal integrals of C1 and equal symplectic areas. So, well, it's hard to integrate C1 over a disk. So what we usually do, we clutch them. Get a sphere and require both integrals to be 0. So this is C1. Now, this makes the Floer complex of H. Now, with this convention, the action and the index is still well defined. So the Floer, and therefore we have the filtration and everything. The Floer complex is then a module over the quotient of pi2 by this equivalence relation. So in other words, this is the quotient of pi2 by the simultaneous kernel of C1 and omega. Now, strictly speaking, one in the most general case, one has to complete the Floer complex here, and so one usually thinks about kind of as this group is simply the group of recappings, the group of changing the disk. But if I want to think in terms of the coefficient ring, I should take the group ring of gamma and ideally complete it. One important point which is somehow not emphasized is that in many cases, actually, you don't need to complete. For instance, if the manifold is monotone or negative monotone, actually, or if the minimal churn, I think, is large enough, actually, you don't care to complete. The kind of, when you look at the construct, something I actually did not realize till someone pointed out to me just this, you don't need to do the numerical completion in this case, but in general, you need to complete. So then there are many technical difficulties to overcome with compactness. To define the Floer homology, which I'm not going to talk about. Either one has to make additional assumptions or use with virtual cycles. There are experts here, and I am not. But one thing to keep in mind, that which is kind of immediately relevant, unless omega is rational, this construction does not go through. At least not so obviously. at least one has to make some further, I would say, conventions. The problem is that once omega is irrational, the all possible values of omega on gamma are dense in R. So the effects of recappings are, well, by recapping, you can actually you can create a dense set of critical values out from one critical value. So the action spectrum is always dense. The endpoints of the interval are never sort of separated from the action spectrum. And the right-hand side becomes immediately very sensitive to the nature of perturbation. So one actually has to be careful how to perturb it, and arbitrary perturbation does not work. So it's simply not well defined. So that's something to keep in mind, and that's something Doris, when proving the degenerate case of the Conley conjecture, had to sort of sort this issue out. Now I'm going to say something not entirely new, but perhaps when you think of it being done in a systematic way, relatively new. Local Floer homology. So let X be an isolated one periodic orbit of H, possibly degenerate. And actually, I'm interested in the case when it is degenerate. Let's take a small perturbation of H twiddle. Under this, so I want it to be non-degenerate. Under this perturbation, the orbit X is going to split into several non-degenerate orbits. Maybe 0, maybe 1,000, but some number. So this is X. These guys, X1, X2, etc. The number could be 0. It could be 0 in much worse ways than this, but yeah, it could be 0. Now, kind of, it's a standard exercise in Floer theory to show that whenever I look at these orbits X splits into, a Floer trajectory connecting any two of them is actually contained in a small neighborhood of X fixed in advance. I'm fixing U, taking a small, perturbation, so non-degenerate depending on U. And observe that all Floer trajectories connecting these guys are contained in U. And the reason is that if I want to, the reason basically is that X is an isolated orbit. So if the Floer trajectory wants to get close to the boundary of U, there are no periodic orbits anywhere here. And a behavior like that requires a lot of energy, or at least some amount of energy. So it requires energy below a certain threshold. On the other hand, the energy here is different by the bound, is equal to the difference of actions. So this is x3 and x4. And this difference is approximately 0 because both of them are approximately the action on X. So there are things to prove here, but that's a pretty standard exercise. So as a result, we have a Floer complex of X, and strictly speaking, I have to write down the perturbation defined. So this is the complex generated by these guys and with the ordinary Floer differential. And then the continuation, well, the standard continuation argument tells us that actually the Floer homology, let's write just X here, and we remember the Hamiltonian is well defined. Now, this is an entirely local construction. So all I care about is the behavior of H near X. I never sort of need to go away from X itself. Outside. I never need to go outside U. However, what is not quite defined is the grading. The grading requires fixing a frame along X. These guys are close to X, so they inherit the frame, and then the gradient is defined. If X sits in some ambient manifold and I have a mechanism there to create a frame, as for instance, when X is a contractible orbit, then I can use that. But this is kind of a piece of extra data. All right, so that's the local, that's the definition. Now I want to discuss its properties. If H is C2 small and autonomous, and X is a critical point of H, then the log, well, sometimes I will write H here, sometimes I won't. So let me, on this occasion, write it. Then the local Floer homology of this periodic orbit is isomorphic to the local Morse homology of the critical point. And with my conventions, I need to shift degree by 1, so by n. So I think I need to add n here. I have not defined this, but the definition is identical. We just replace an isolated one periodic orbit everywhere by an isolated critical point, and we replace Floer trajectories by Morse trajectories, like take these worms and squeeze each of one into line. So, 2. If I take a family of Hamiltonians with the same critical point, with the same one periodic orbit, then the homology remains constant as long as the periodic orbit is isolated, and to be precise, uniformly isolated. And uniformly isolated, this is what Doris pointed out to me many years ago, that actually you needed to be uniformly isolated. You need to have U which isolates X for all Hamiltonians in question. And here is a counterexample when things go wrong. Okay, so what I wanted to sketch is this picture. But somehow, and this is certainly an answer, but somehow it escapes me how to articulate it at the moment. Sort of just think of this graph. Right, so here is a critical point. This is a maximum. It has Morse homology in degree 1. Here is a minimum. It has Morse homology in degree -1. Let's start, let's grab this part of the curve and start pulling it out. The two critical points will converge, and eventually I get something like x cubed, and it has homology 0. I can deform it further. So this is an example when sort of 2 points converge and cancel each other and kill each other. But and at every given moment, sort of this is an isolated point. However, the neighborhood U shrinks. So you need it to be uniformly isolated. 3. The support of the homology, let me now suppress H, is in delta of x minus n, delta of x plus n. And actually, we can replace the closed interval by an open interval when x is weakly non-degenerate. So at least one of the eigenvalues is not equal to 1. This is an easy consequence of this fact together with the continuity of the mean index. And by saying the support, I just mean the range of indices where the homology is non-zero. The range of stars where the homology is non-zero. So, this is a pretty kind of formal consequence of the behavior of the indices. Nonetheless, it is important. By the way, here's an interesting thing. As I said, the gradient here actually depends on an extra structure. We need to fix a frame along an orbit. But so does the mean index. So when you replace the frame, you acquire sort of a Maslov shift here and in the interval, and this is the same shift. The integral of, well, basically the Maslov index of the. All right, number 4. I think I'm done with the. So assume that the one periodic orbits of H are all isolated. You have finitely many of them. Then the local Floer homology of them are building blocks for the global Floer homology of H. Namely, there is a spectral sequence starting with these guys and converging to the global Floer homology, and one can restrict everything to an interval of actions. What will be important for us is a very particular case of this, that if in some degree, all local Floer homology is 0, then in the same degree, the global Floer homology is 0. Now something non-trivial. So up to this point, it's all kind of entirely predictable. And in some sense, maybe except being sort of set in such a kind of systematic way, goes back to Floer. So I want to, before that, let's do an example. Let's do a trivial example. First of all, if X is non-degenerate, then the local Floer homology of X is Z2 concentrated in degree equal to the Conley index of X and 0 elsewhere. And from 1, it's kind of instructive to look at the following example. Let H be C2 small and autonomous. And X is a local strict maximum of H. And I want it to be isolated as a critical point. Something like that, but possibly very flat. I do not require any non-degeneracy. Then the local Floer homology of X is Z2 concentrated in degree n. By the first property, this is the same as saying that the local Morse homology of the maximum, or which is in the case just the relative, reduced relative homology of the sublevel is concentrated in degree 2n. And actually, if you think a little bit, there is something to prove here. You know, you need to show that actually the sublevel is has the same homology as the disk without any non-degeneracy assumption. So there is actually a bit of work to do here. All right, now something non-trivial. I want to understand the behavior of the local Floer homology under iterations. So let's take an isolated orbit. Let's iterate it and try to understand what can happen to the local Floer homology. An immediate question arises. You know, to have the local Floer homology, the orbit has to be isolated. If X is isolated, how do I know if this is isolated? And the example of rotation in pi over 2 in pi shows that the second iteration of an isolated orbit doesn't have to be isolated. So let's introduce some terminology. So this is next little chapter, behavior of this function k to hf star k. Let's introduce some terminology. Now again, we are getting some non-trivial overlap with Bashak-Stock. By definition, I say that k is admissible if all right, I'm going to say it in several ways. If X, if the kernel of d phi at X minus, so if the multiplicity of 1 as a generalized of eigenvalue of, or as a generalized Floer multiplier of X is the same as for X to the K. So if the dimension of the, if the multiplicity of 1 as a generalized eigenvalue of d phi is the same as multiplicity of 1 as a generalized eigenvalue for, let's write 2n here. This is enough. As a generalized eigenvalue of the case iteration. So here is an example. Here are a few examples. Let's, or maybe an equivalent formulation. K is admissible if K is not divisible by the degree of any root of unity among the eigenvalues of d phi. Examples. So no roots of unity among the eigenvalues. No Floer multipliers a root of unity. And this is a condition of strong non-degeneracy, simply meaning that x to the k is non-degenerate for all k. Then all k are admissible. The second situation is the opposite. X is totally degenerate. So all eigenvalues are equal to 1. Then it's already as bad as it could get. You cannot get new eigenvalues equal to 1. So again, everything is admissible. And finally, no matter what, all large primes are admissible, because x can have only just so many eigenvalues, so only so many prime numbers can occur there. So all large primes are admissible. A theorem. X is isolated, and I'm going to assume that K runs through admissible iterations. Then the local Floer homology of X and the local Floer homology of the case iteration, well, kind of before that, even before that, let's get to that. Then x to the, so x is isolated, k is admissible, then x to the k is automatically isolated. This is not really important for what follows, because when something is not isolated, we get infinitely many periodic orbits on the nose. But it's a kind of a peculiar fact. Then x to the k is automatically isolated. And the local Floer homology of x and x to the k are isomorphic up to shift of degrees. Moreover, I have some reasonable control about what happens to this shift of degree. The shift divided by k goes to the mean index of x. And if x is totally degenerate, or so all eigenvalues are equal to 1, then the shift is equal to just k times the mean index. When x is totally degenerate, the mean index is necessarily an integer. So the way we should think about it, this is the mean index of x. This is the interval, the mean index of x plus minus n. So this support, the homology is of x is somewhere here. And then as I iterate x, this interval without the homologies just gets shifted to the right more and more, provided that the mean index is, say, positive. Or to the left if the mean index is negative. So it's just the picture replicates itself identically up to the shift. So what happens here happens exactly there for the next admissible iteration. Then for the next one, etc. Now, I should mention something here. We did not know it till sometime later. The fact that x to the k is automatically isolated is not new. It's not widely known, but sort of this persistence of isolation has been known for quite some time. But I don't remember now who proved it. So again, we think about this theorem as a kind of persistence of local Floer homology. If you have, at least that's one way to think about it. If you have non-zero local Floer homology, it will stay non-zero for all admissible iterations. So, of course, there can be some non-admissible iterations. And then we don't know what happens. But an easy corollary, maybe not exactly of the theorem, but of the proof. So you see, let's assume that the point is isolated for all k. Would be enough to require it to be isolated for some finite range of k. Then the function k goes to the local Floer homology. Let's send it to the rank, to the dimension of the local Floer homology. Is periodic. And the proof of the corollary, you kind of so let's say x has roots of unity of degree 3 among its eigenvalues, among its vacuum multipliers. So then k is admissible either for x or for x cubed. So by applying this theorem to x and x cubed, we see that this function is periodic. For like, if everything is admissible, this function would be constant. What's more important? One consequence of this fact, it's actually not immediately obvious, that the amount of homology you can pack in one orbit cannot grow with the order of iteration. So an example of the, let's do an example. You can squeeze it in here. I meant to do it, it maybe more belongs to this part. So example 3, let H be the monkey saddle. Something like that. The real part of z to the n. Then I think the local, and I can think of the origin as either a critical point or a periodic orbit. In either way, the Morse homology, let's say the Morse homology is 0 in degree 2, 0 in degree 0, and this is a saddle. And something like Z2 to M in degree 1. Don't take this M literally. It may be M plus 1 or something like that. The important point is that it can be very large if the saddle is too monkey, is very monkey. Now start iterating. So originally it can be very bad. But as you start iterating, it cannot get much worse. In this case, it cannot get any worse. You are packing the m-dimensional homology in one point, and you cannot pack anything more than that into the iterations of that point. So I'm going to actually say a couple of words about the proof of this theorem, but maybe first I want to mention some related results. So if you remember, I mentioned a theorem, sort of related results. If you remember in the first lecture, I said that for many Riemannian manifolds, you very easily get infinitely many closed geodesics. And you get infinitely many closed. So here is a theorem, Gromel and Mir. Whenever the rank of the homology of the loop space grows, and this is a loop space of some Riemannian manifold B, B has infinitely many simple, or prime, as they say in Riemannian geometry, closed geodesics. This is immediately obvious when, so this would be the case, for instance, for B S2 cross S2, or the product of two spheres of any dimension. So this would be immediately clear in the non-degenerate case, because to generate this infinite complex, you need infinitely many generators. In the non-degenerate case, you need to work a little bit. And what could go wrong is that you have one simple geodesic, and the amount of homology you pack into, but then, of course, once you have a prime geodesic, you have all its iterations, and you get more and more homology into that, into the iterations of this geodesic. So there is a very similar theorem due to Gromel and Mir that actually says that it does not happen. Then whatever Morse homology of a closed geodesic you do, it cannot actually grow. So similar results. So starting with Gromel and Mir for Morse and geodesics. And then if you take this theory, if you go into the realm of contact geometry, if you take a closed Reb orbit and you can associate to it a closed Reb orbit, you can associate to it either local contact homology or local symplectic homology, provided that the Reb orbit is isolated. And that local whatever type of homology you do, it's actually closely related to the homology of the return map. And so when you apply this theorem to the return map, you obtain a similar result for the local symplectic homology or local contact homology. And this is MacLean and Hrinevich and Maccarini, who extended the result of Grommel and Mayer to the contact, to the rep context, whenever you have the growth of the underlying global homology, contact homology or symplectic homology. So this is a couple of related results. Now, a remark on the proof. The proof is actually quite easy. So let's look at two particular cases. One particular case is when all x to the k are non-degenerate. So the strongly non-degenerate case. Then nothing happens. Then hf of x to the k is z2 in the degree of mu Conley-Zender of x to the k. So the shift in this case is, so in this case I have to take the shift to be sk, the difference of the Conley-Zender indices. You have 1 point here, and it sort of repeats itself. The second case is when x is totally degenerate. Then, well, all eigenvalues are equal to 1, then phi is close to the identity near x. In all these questions, actually, it's convenient to think of x as a constant orbit. And x can be turned into a constant orbit by applying a loop or a local loop. So it's just more convenient. In some sense, this picture I raised here with x represented by points was could have been taken literally with the orbits being points. So x is totally degenerate, then phi of h is close to the identity near x, and then I can sort of, then near x, passing near x, I can think of phi as given by a generating function. Just in the very classical sense, I pass to the diagonal in the square, identify a neighborhood of the diagonal with the square with the tangent bundle, then the graph of phi is very close to the diagonal, so it becomes the graph of some generating function df. An analog of the very first property tells me that the local Floer homology of x is isomorphic to the local Floer homology of the generating function. Sorry, local Morse homology of the generating function. Up to a shift of degree. But the same construction applies to x to the k. Phi to the k is again close to the identity. So but what generating function can I possibly expect for x to the k? It will be kf. And the local Morse homology of f and kf are obviously equal. So in this case, one has to be careful about the choice of frame, but with sort of the choice of the trivial fixed frame here, implicitly in this picture with these conventions, actually you don't get any shift. The homology just remains constant. One has to work here a little. Yeah, the size of the actually there is even a more serious catch here. The size of the neighborhood will shrink. It's still okay because evaluating this thing, I can shrink. There is something worse that can happen here, namely, x can be totally degenerate without the Hessian actually vanishing literally. I'll talk about that later. So actually, there is some work to do here, but sort of when I went to Yasha and told them about the sort of theorem, he kind of thought for a second, said, yeah, it's obvious. and then he sort of outlined the proof, and that was like pretty much this. And there is a third step. The third step is the product of these two. And of course, dynamics of H near fixed point does not have to split. But it has to split up to a homotopy which keeps x uniformly isolated. So you can always split x after applying homotopy to it into a product of something totally non-degenerate and totally degenerate. This is the outline of the proof. Now, maybe before I move on, I want to say what, as far as I understand, what is completely unknown here. What is completely unknown is what happens if I do an inadmissible iteration. Let's say k is not admissible. X is isolated. X to the k, let's assume it to be isolated. So now I have the local Floer homology of these two guys. So we can think of the example where phi is the rotation in 2 pi I divided by k plus higher order terms. And if you choose your higher order terms right, these are conditions. These conditions can be easily satisfied. So what I don't understand at all, what can happen in this transition. So it's very easy to see that here you can have something small, and there you can get a monkey saddle. But sort of I even would not know how to ask the question exactly, but sort of this transition, what happens when you go through an inadmissible iteration is completely not understood. Are there any relation between these two? Say I start with something non-zero, can I get 0? So that's the simplest question we don't know how to answer. So this is non-zero. Can I have possibly 0? All right. Now I'm done with all the preliminaries, and we are ready to go to make the next step and start proving the Conley conjecture. So let's recall the theorem. This is the Calabi-Yau case of the Conley conjecture. Assume that the first Chern class vanishes on pi 2. The fixed point set of H is finite. Then, for every sufficiently large prime K, there exists a simple K periodic orbit. The two corollaries. The first one is that the number of simple periodic orbits is infinite, because either this fixed point set is finite, then the theorem applies, or it's infinite, and then you're done. The second one is that under the hypothesis of the theorem, you have the growth. And the growth is of the order k divided by the log of k minus a constant, the number of primes less than or equal to k. Sorry, yes. Growth is not exactly that. It's actually very interesting. It would be, one can improve this slightly. It's actually strictly faster than that. But so the ratio of the growth by that goes to infinity. But it's absolutely unknown. So one could expect actually linear, at least linear growth here, but it's absolutely unknown actually. How to prove it. So the key notion is an SDM. I introduced this term, although the notion sort of goes back to Kinston. It means symplectically degenerate maximum. This is an awful term, but it's too late. It's kind of stuck. So let's define. Let X be a periodic orbit. Well, so far, like, it doesn't have to be simple, but not necessarily simple. I say this orbit is an SDM if its local Floer homology in the degree the mean index plus n is not equal to 0. So if you remember, the local Floer homology is supported in the interval delta of x minus n, delta of x plus n. So I require it to be non-zero at the rightmost. This is the mean index. X is possibly degenerate. So the local Floer homology is somewhere here. So I require it to be non-zero here. So we also remember that the inclusion is actually into the open interval when x is weakly non-degenerate, when there is an eigenvalue not equal to 0. So the only way this can happen when all eigenvalues are equal, so eigenvalue not equal to 1, sorry, when all eigenvalues are equal to 1. A consequence, an immediate consequence of the definition is that sort of a remark, x is SDM, implies that sort of let's say x is totally degenerate. Now, before I get to the proof, I want to study the symplectic degenerate maxima, and I want to do like the easy part. There will be 2 iterations of that. I want to do the easy part. We can forget about the Conley theorem for the time being. Example. H is autonomous. X is strictly degenerate maximum, meaning the Hessian of H is equal to 0. And I want it to be isolated. Then X is an SDM. This is one of the examples I had on the board. All the same. But now, rather than requiring the Hessian to vanish identically, I'm going to say that, so H is autonomous, X is isolated max, and I say eigenvalues of the Hessian are equal to 0. And then again, X is an SDN. And this is something I want to discuss a little bit. What's the difference between a quadratic form being identically 0 and having 0 eigenvalues? And we are in the symplectic universe. So, a little discussion. Let's say V is a symplectic vector space, R2n. Q is a quadratic Hamiltonian. So when I just stare at the quadratic form in the presence of a symplectic structure, I cannot diagonalize it. So by definition, let's do it this way. By definition, the eigenvalues of Q are the eigenvalues of the Hamiltonian, of the linear Hamiltonian vector field generated by Q. This is just JQ. So it's entirely possible for a quadratic form to have 0 eigenvalues. Huh? No, the gradient of Q is, I think, Q itself. And so the gradient, the matrix of the gradient is the matrix of Q up to 1/2, I suppose. So this is the symplectic gradient. This is the symplectic vector field of Q. So if V is R2 with coordinates P and Q, and the quadratic form Q is, say, Q squared or P squared, then the symplectic vector field it generates is 0, 0, 0, 1. So it's a Jordan block. It has 0 eigenvalues. The Hamiltonian vector field, so when I look at the origin as a fixed point of this Hamiltonian vector field, or this Hamiltonian flow, it will be totally degenerate. All eigenvalues then. So the flow will be 1, 1, 0 time. So this will be the shear flow. So from the symplectic perspective, this is a very degenerate thing. But nonetheless, the quadratic form itself, the Hamiltonian itself, is non-zero. So in this case, this is not an isolated fixed point. It's not an isolated critical point of Q. But I can make it isolated by adding higher order terms. So an example here would be P squared plus Q to the fourth minus. An example in this case would be minus P to the fourth plus Q to the fourth. So this is still an SDM. I want us kind of to. So in this, this Hessian is non-zero. And what this says is all eigenvalues of the Hessian are 0. All eigenvalues, the Hessian is p squared, and the eigenvalues of the Hessian are 0. Eigenvalues of the Hessian are these two zeros. Eigenvalues of the Hessian are, by definition, the eigenvalues of the vector field generated by Q. A symmetric matrix doesn't have eigenvalues. And so, okay, the Hessian is a symmetric matrix, but a symmetric matrix does not have eigenvalues. To talk about eigenvalues of a symmetric matrix, I know. This is the definition. The eigenvalues of a quadratic Hamiltonian are the eigenvalues of the vector field. So sort of this is the standard definition in mechanics. So the eigenvalues of the linear Hamiltonian vector field generated by this Hamiltonian. Sort of when you go back to classification of quadratic Hamiltonians, it will be sort of classified. I mean, the first input thing. No, I call this a Hessian. And I call this, guys, the eigenvalues of this Hessian. Yeah. No, the Hessian doesn't have eigenvalues. A quadratic form just by itself doesn't have eigenvalues. But so when you have a quadratic form on a symplectic vector space, by definition, its eigenvalues are the eigenvalues of the vector field it generates. Sort of when kind of you take something like Arnaud's book on classical mechanics, or I don't know, like old papers on classification of quadratic Hamiltonians, it will start with the eigenvalues of these quadratic Hamiltonians are. And that's actually what they mean. So that's, it's a terminological remark which is kind of invariably confusing. And when you say eigenvalues of the Hessian, first you think that eigenvalue of this thing is 1, then you think that this thing does not have an eigenvalue. But actually what they mean is that, or what I mean is. Now, there is a remark here. By symplectic linear transformation, stretching in one direction and squeezing in the other, I can turn this Hamiltonian Q into epsilon p squared. So in fact, I can have epsilon here, I can have epsilon there. So it's actually, even though it may be quite sizable to start with, by making a linear transformation, I can make Hessian arbitrarily small. I cannot make it 0. But by applying linear transformation, I can make it arbitrarily close to 0. So this is something which kind of, the fact that it can be non-zero is trouble. The fact that I can sort of make it arbitrarily small is a solution. So it pops up here. If you start with X totally degenerate, it actually does not tell me that it's close to the identity. In fact, it does not have to be necessarily close to the identity. The Hessian doesn't have to be small. But I can make it close to the identity by applying a linear transformation. And so it actually comes up already here. Huh? Yeah. The size of the neighborhood, this is trouble. The size of the neighborhood changes. Yeah, but it's not that much trouble for the calculation of local Floer homology. I can sort of start with a very small neighborhood. It's something to keep in mind. Yes, indeed. So I'm not going to worry about this much, but this is actually a complication. Now, so that's an example, or just we want to keep in mind that we can always turn it into something like epsilon p squared plus 1 over epsilon squared q to the fourth by a linear transformation. And yes, indeed, it is kind of clear from that that to make it small, we need to resize the neighborhood. All right, that's but once I make it small, I can equate the local Floer homology and a local the local Morse homology as in one of the properties, and I see that it is actually concentrated in the top degree. So these are two examples to keep in mind, and it's actually probably a good moment for me to stop because